On the topic of iterated integrals, we talked about Fubini's theorem. Now I expect you to ask, what if we have more general regions? What are we going to do? We're going to divide this up into two cases. If our x is bounded between two fixed values, the outer integral is going to be with respect to x. And your inner integral is with respect to y. Why? Because y is changing between two functions. And if your y is bounded between two fixed values, c and d, it acts as the outer integral. And your inner integral is with respect to x because x is changing between two curves. Example for you. Suppose I ask you to calculate the double integral of x squared y dA, and D is the region given in the figure below. Y is equal to square root of x, and y is 1 over x. So you have a radical function, and also you have a reciprocal function. The intersection between these two is at 1, and then on the right-hand side, the region stops at 3. So we have so far these pieces of information. And the region is highlighted here for you. But again, please note that your x is bounded between two fixed values, 1 and 3. Your y from top is bounded by square root of x, and from below, it is bounded by 1 over x. So the lower bound for your function y is 1 over x, and the upper bound is square root of x. Now let us set up the integral. Since x is bounded between 1 and 3, the outer integral is with respect to x. And your inner integral is going to be with respect to y, because your y is changing. So your inner integral, again, is with respect to variable y, because your y is changing between two functions. Remember that from elementary calculus, the integral of u to the n du is u to power n plus 1 divided by n plus 1. We're going to apply this rule here for the integral of y dy. X acts like a constant in this case. So you have a half x squared, y squared, and y is bounded between 1 over x and square root of x, which in turn can be written as a half x squared, square root of x to the second, minus a half x squared, 1 over x to the second. We just plug in the upper bound and lower bound, and we find the difference between them. You can simplify this as a half x cubed minus a half x squared, and 1 over x squared, they get canceled out. Very good. So we calculated the inner integral, which is a half x cubed minus a half. Now we're going to calculate the outer integral with respect to x. This is equal to 1 over 8 x to the 4th minus a half x. X is bounded between 1 and 3, which is 69 over 8 minus negative 3 over 8, or 9. So the double integral of this function over the given region is 9. Or you can say that, hey, the volume bounded between x squared y over the following region is 9. In this example, we're going to discuss how we choose a convenient integration if you have x and y involved. Sometimes it makes it a little bit difficult to take one integral over the other one. In this case, we have the integral of y e to power xy dA, and the region is given to you as x is bounded between 0 and 1, and y is bounded between 0 and ln of 2. If you try to take the integral with respect to y first, then it requires integrating of y e to power xy with respect to y, which has integration by parts. So if you feel comfortable using integration by parts, well, it's going to be easy for you. But we have another approach, which is a little bit easier. You can take the integral with respect to x first. So you have the integral of y e to xy dx. X is bounded between 0 and 1. Then you take the outer integral with respect to y. We're going to evaluate the inner integral with respect to x using the integral of e to the u du, which is eu. Take u to be xy, which is the exponent. Du is y dx, which you already have. So your integral is e to xy, and it's bounded between 0 and 1. Then you take the outer integral with respect to y. Well, the rest is just simple calculation. The definite integral 0 to ln of 2 of e to the y minus 1 with respect to y is e to the y minus y. Y is bounded between 0 and ln of 2. So when you substitute ln of 2 and then 0, you get 1 minus ln of 2. So in this case, it's not that difficult. You can take the integral by parts and calculate the integral. Or you can switch between x and y, but please make sure that you are switching the boundaries as well. Please note that you have fixed boundaries here, so you're allowed to do this easily. But if you have boundaries that are changing, that are dependent on a variable, you cannot do this like this as easy as you see. We have to make some adjustments, calculate the boundaries, and then make those changes.